All right, good afternoon, everybody. It's 2 o'clock Eastern Time, and we are going to go ahead with a OpenVSP structures modeling demonstration with Justin Gravitt at ES as a reminder, please set your video player quality to 1080p so that you can see the screen nice and clearly. And if you guys have any questions or comments, by all means post those to the social Q&A that you can find on the main page or link directly below your player. Or you can post things in the YouTube live stream chat there to the right of your player. So with that, I'm going to go ahead and move the Teams meeting over here so you guys can see it and go full screen. And then, Justin, I believe you are ready to go, sir.
All right, great. Well, thank you. So what I'm going to be talking about next is the structural modeling capabilities and FEA mesh export capabilities available in OpenVSP. So this was done as part of a SBIR effort funded by the Air Force Research Lab, which is also funding OpenVSP. So this was done a few years back. It's had some minor changes and updates since then. There are still more improvements that may come, but this is just what you can do in OpenVSP. I'll walk through the just basic concepts of the terminology that we use, what sort of capabilities that we have in OpenVSP, the implementation approach. Then we'll go through the typical workflow. We'll walk through the GUI, all the different FEA part types, which are structural entities, just another word that we call them. We'll do an example analysis. I'll talk about the CAD exports. So that's been something that's been updated more recently through our latest funding effort. I'll briefly talk about API and scripting. More details on that, you could see the previous presentation I did. And then I'll walk through a demo. Please use the YouTube live chat stream to ask any questions that you guys have, or if you'd like to see anything in particular, or use the conference.io link that's on there as well. So when we initially set out to add this capability to OpenVSP, we wanted to just support modeling of aerospace structures and FEA mesh generation. This was actually something that there was a capability for in version 2, but we wanted to bring it to version 3 because it had been left behind and just improve it from there. The features that we have available, we have parametric modeling of full depth structural members. So that means things like ribs and spars that go all the way through the OML. You can use subsurfaces to model different areas of your structure. We have beam and shell elements. Those are the two FEA elements that we support. We have key point identification, so that, which I'll describe more in detail later, places a node at a specific point on the surface that you would like it to, and that can be used for attachment points, point masses, things like that. We have exports to Nastran, Abacus, or Calculus in Gmesh in these FEA mesh formats, but also you can export step and IGES if you want the analytical surfaces. So like I mentioned earlier, there were some capabilities for structural modeling in version 2. You could only have, excuse me, you can only have one structure per vehicle. It only worked for wings with ribs and spars, and you only had shell elements. There wasn't any material property assignment, anything like that. You also couldn't include point masses in your mesh. So in version 3, we've brought all of that capability to start and then improved it, like I said. So we have multiple structures for multiple geometries. So a single wing could have dozens of structural models associated with it, and you can pick and choose which one you want to export. We don't only support wings. You can have, like you see at the bottom right there, a fuselage. We have a variety of FEA part types. So instead of just ribs and spars, we have bulkheads, or dome as we call it, just generic slices. We have subsurfaces, fixed points, things like that. Instead of just shell elements, which are the triangulated surface elements, we have beam elements too, which are border curves, intersections, things like that. Subsurface edges, things like that. We have a complete materials and properties library, so you can add your own materials and properties and assign your shell or beam elements to those properties. And then we have tools for visualizing the mesh. And then, like I said too, we have a point mass as a fixed node in your mesh, wherever you specify. So the structural entities that we support, we have full depth entities. So those are ones that pass completely through the OML. Examples are ribs, spars, floor, bulkhead, things like that. And those are a shell type of structure. We then have zero depth. So those are things like stringers, stiffeners, longerons. They have cross-sectional properties associated with them. And they take the form of subsurface edges or intersection curves, and they're represented as beam types. So we have shell and beam types, and then we also have key points. So a key point is going to be a corner of the triangulated mesh, so where the corners come together at a specific point that you specify. This is used to provide connectivity to other structures, which is really important considering that we can only have a single structure on a single geometry at a time. So you can't have a structural model of your wing and fuselage. You have to have one of your wing and then your fuselage separately. These key points allow you to potentially connect those together in separate tools. We don't support partial depth structures for the most part. There is some limited capabilities in terms of having ribs and spars that are only confined to a certain section of your wing, things like that. But for the most part, we don't support partial depth structures. Those sort of things are going to be like an open frame, a stiffener that doesn't go all the way around the OML, things like that. So this is identifying some of the terminology that we use in OpenVSP. So to start off, we have a structure or an FEA structure. That is a collection of FEA parts. As I mentioned, you could only have one structure. Each structure can only have one parent geometry, but you can have more than one structure for a given geometry. An FEA part, those are structural entities. Those are things like ribs, spars, everything like that. Even subsurfaces, those are all structural entities or FEA parts. It includes the full depth, no depth structures, and key points. FEA elements are those connections of nodes. So when you triangulate the mesh, every triangle is an FEA element. Each corner is an FEA node. So those are used to build up the elements. Nodes are assigned to multiple elements. And so a node might be adjacent to multiple triangular elements. And then we have shell elements, which are the triangulated surface elements. Those are going to be full depth. And in Nastran, that's the C-Tri-S6 type. Or in Abacus and Calculus, that's the S6 type. So 6-node triangular elements. So we also include, if you see on the right here, we also include the midpoint of each segment of the triangle as part of that 6-node element. Beam elements are going to be the zero depth elements. So we also call them caps. Those are going to be the C beam type in Nastran, or in Abacus, the B32 type. The right image gives you kind of overview of these different this different terminology that we use in OpenVSP. So here's the typical workflow, and I'll walk through the GUI that follows this. So you first have to have a geom You then go to Analysis in FEA Mesh. You add a structure to that geom or any other geom that you have. There are optional settings, so you can add up or create your materials library, and you could also create a library of properties and assign materials to each properties. The mesh settings can be adjusted, and your output files can be specified. But you can also just go with the defaults. Then once you have your structure, you can add FEA parts to it, modify their parameters, and then once you're all ready, your structural model is complete, you click Mesh and Export, or, which I didn't mention on here, you can click the Export CAD button. Then you can visualize the results, the intersection curves, things like that, the triangular elements, and then you can take those exported files, your step and IGES file, your Nastran file, things like that, and import them into any of these external tools that we support. So jumping into the FEA Mesh GUI, this is showing the first tab. So at the very top, we have a link to the wiki documentation, so easy to access there for new users. We then specify the unit system, and that just makes sure it basically just is the what's written out to the file, the export files. It keeps everything consistent. When you change your unit system here, it'll automatically update your materials and property settings to it'll convert those automatically. So that's what that's used for. We have a browser that lists all of our structures, but the first thing we have to do is add a structure for it to show up there. You can specify which geom you'd like to add a structure to, and you could add a structure to anything that has a surface. So you can't add it to a blank, but you can add it to an ellipsoid, body of revolution, whatever else you like. I don't believe you can add it to a mesh geom either. Pretty sure about that. So the surface selection is if you have a component with multiple surfaces, so that that surface index is for main surfaces. So if you have a propeller, the default propeller is 3-bladed, you could add a structure to any one of those blades. You can't add a structure to the entire 3-bladed propeller. If you have structures in this browser, you can click on them, and that'll update at the bottom what your current structure is. If you also have one selected, you can click delete to remove it. For body components, and this is what's shown when you have one selected, you can basically just show the degen geom preview. So top, front, top, side view, those are those options there. For a wing geom, we just have a top view. So that's going to show a top-down view of the degen geom preview. If you'd like to get back to your regular 3D view, there's options in the geom browser to go back to that. I can point those out later. Going to the part tab, this is where you're going to be adding structural entities to your FEA structure. So this will, when you first add a structure, all this will have is the skin on the top line. So that's the outer mold line. That one, the only option that it has is to remove the skin tries. So, or remove the skin on export. So that would just leave, if you have a wing with ribs and spars, it'll remove the OML from your export. That's really the only setting you can change on it, other than its property that's associated with it. Next, what's going to be listed in that FEA part selection browser are your just standard FEA parts, like which I'll go through in a little bit, which does not include subsurface types. So ribs, spars, slice, dome, things like that. Those will all be listed next. Below that, you'll have subsurface types. There's options to reorder things in that browser. Primarily, that comes into play for subsurface types only. And what that does is when you have overlapping subsurfaces, the order that they appear in this browser will dictate how elements are assigned to the overlapping sections. So that's what that's used for. In the middle, we have the type of FEA part that we'd like to add to this browser. Once you add it, it'll pop up a new window with parameters to edit things. If you close that or want to select a different one, you could also select it and click the Edit Part button. You can delete any part that you have selected. You can also use the Shift and Control keys to highlight multiple parts at the same time, and you could delete multiple at the same time. I believe you can only edit the name of a single one at a time, but that's what this next entry is for, changing the names of your FEA parts. Under General, which you can do with multiple at the same time, you can set it to a shell, a cap, or a shell and cap. So if it's a shell, we're going to have the triangular elements saved in the mesh. If it's a cap, we're just going to have the intersection curve saved. Shell and cap will have beam elements along the intersection curve or the subsurface edge, and we'll have the shell elements that make up the actual surface. You can assign properties to your shell and cap elements there, and then you can show or hide the FEA parts from the 3D view. So the first FEA part type that we have, which is sort of the basis for some of the other ones like ribs and spars, is the slice type. So on the left here, we have the GUI that's associated with that specific FEA part type. So you can change its orientation. We have a few options there of how you'd like it to be oriented. You can set the distance as relative or absolute, relative along the axis that you specify under orientation. Rotation axis you can specify as well. You could just do a single rotation at a time. And then at the bottom, this is pretty much standard for every different FEA part type. You can specify the elements that you want to include and their properties that are associated with them. So next we have wings and spars, which are only available, ribs and spars that are only available for wing type geometries. So the rib's going to be defined from the leading edge to trailing edge automatically. It's just both of these are based off of the slice type, but they're just parameterized in a way that makes a little bit more sense for ribs and spar type modeling. For ribs, you can specify, and this has been slightly updated since this image was put in here, but you can specify if you want to be the rib to be normal to the leading edge of the wing, the trailing edge of the wing, or any other FEA spars that you added as well. So if you have a leading edge spar or a trailing edge spar, you can set your ribs to be perpendicular to either one of those. Limiting rib to section and also limiting spar to section, that means that you want that FEA part to only be in a section of the wing if you have a multi-section wing. If it's placed along the edge of that section, it'll be automatically trimmed. So I'll give an example of this, but one way you can use this for is if you have a multi-section wing, you can place one spar in the first section at one location, and then place another spar in the second section at the same location, and those will be at a different angle if you have changes in your wing sweep or anything like that, but they'll still be connected at that change in the wing section. I'll demonstrate that and explain it more a little bit later. For both of these types, you can specify the distance as relative or absolute. You can specify a rotation. So this is going to be just a rotation about, I believe, the z-axis for a wing. See, one limitation here that we have at the moment is
Justin, are you still there? Well, we might have lost Justin there for just a minute. Let me see if I can get him back online, and we'll see if we can't get this started back up.
I've changed my internet that I have selected. Hopefully it's a little bit better this time. Do you know which slide I was on before
You
that
were on this
disconnect?
slide.
I was on this slide. Okay, good. Okay. So sorry about that, everyone who's been listening in. Hopefully that doesn't happen again. But um, going back to this presentation on FEA structural modeling in OpenVSP, the FEA part for rib and spar, you have some capabilities to limit it to a certain section, if you like, of your wing. You have some capabilities to change its rotation. One limitation is if you have dihedral in your wing, you don't have the ability to really line up your rib with your dihedral. That's something that could be improved in the future. There is a workaround, and I'll explain that a little bit later. But this trim to bounding box option, you can select that if you'd like to trim the FEA part just to the leading and trailing edge of the wing. Otherwise, it'll trim it to the entire bounding box of your wing. That's mostly used if you have some weird things going on where you have a really sharp change in angle between two ribs, and they are extending out, and you want to avoid that intersection. Things like that. Most of the time, you can just leave it on by default. XYZ location and an XYZ rotation. You can attach it to the spine of your component. It's only used for body type components, so you can't have it on a wing. And you just basically oversize it. It'll intersect and leave what you can see there in that image behind. So fixed points are next. So this one's really cool. You can specify in UW coordinates a particular place on a surface that you would like the mesh to hold. So triangles will be connected to that node. That node won't be in the middle of a triangle if it's all done correctly. You could also specify the parent surface, so it's going to default just to your OML, but you could also put it, if you'd like, you could put it on a rib, a spar, anything else you'd like. You could also assign that element, that point mass, and that'll be written out to the file as well, using the unit system that you specify on the first tab of the GUI. So then we have subsurfaces. So all the subsurface types that you have for normal geometries, not for structural modeling, those are also available for structural modeling. So we have the line, the rectangle, and the ellipse. Those are available for every geom type. Control surfaces are only available for wing types, but same sort of parameterization as how you would model subsurfaces normally. So example for the rectangle, which is, the ellipse that's shown here in the middle, you have your center U and W, you have your U and W length. If anyone needs clarification about how U and W works, please feel free to ask, but it's that 2D parameterization that we use throughout OpenVSP. One thing to note here is there's an option to do cap and no tries. What that is going to do is only keep the edges of your subsurface and delete everything that is actually the triangles associated with that subsurface. So this allows you to do things like punch a hole in the side of your OML, other things like that, make an access panel, anything else that you'd like to do. So that's what that option is there for. The next FEA part type that we have available are array types. So this just allows you to add a lot of ribs, slices, or line type subsurfaces all at once using a fixed spacing, anything like that. You could have the distance in relative. That would be a fixed number of parts in that array. Or you can keep the distance as absolute, and that'll keep the spacing between the parts constant. So that's what those capabilities are there for. You can click an individualize button for all these different array types, and that'll take your rib array, convert it into a bunch of individual ribs. You can't go back from a bunch of ribs to a rib array, though. Next tab we have is the Materials tab. And so the Materials and the Properties tab, those are available for all structures, so you don't have to have a structure selected. It's just a library that you can then, once you have a structure with FEA parts, you can assign these materials and properties to any that you like. You don't have to create a new material library for every structure that you add. So that's what this is here. We have just a couple of example default ones, but you could just click the Add Material button. They're specified by their mass density, elastic modulus, Poisson ratio, and the thermal expansion coefficient. Like I mentioned earlier, the units on these are going to be converted just however you set your unit system on the Structure tab. Properties. Each one of these properties is going to be assigned a material from that previous tab. So you could have beam type or shell type properties. Those are going to correspond to shell type elements, your triangle elements, or your cap or beam type elements, which are your intersection curves and your subsurface edges. Shell property, all it has is a thickness associated with it and the material, of course. Beam properties, we have a couple of different options. You could do a general cross-section type. So that's going to be specified by its area, moment, and products of inertia. Or we have some standard types of circle, pipe, rectangle, box, things like that. There's a little show XSEC button here. If you click on that, it'll identify which dimensions we're talking about when we just list out dim1, dim2, dim3 as parameters. So that's what that'll show you. Next one here is the Mesh tab of the FEA Mesh GUI. These options are identical to the mesh settings for CFD Mesh. So if you like details about those, there's some good documentation on the wiki, but also feel free to ask as well. These mesh settings are specific to each structure. Be careful if you're working in a different scale of your model than what the default size of the wing is in OpenVSP, things like that. You'll probably want to adjust your mesh settings. So if it's taking forever to run and you haven't adjusted your mesh settings, it might be because your model is very large and your triangles are extremely small. So try to avoid things like that. Test along the way and try to make sure your mesh resolution is close to what you want. You could always start coarse. It'll go a lot faster, and then refine it as you go. There's a half mesh option there. So if you have symmetry, this should make it go about take half as long to execute. There was a bug that was fixed recently in the half mesh option. So this fixed a few versions ago. It should now actually be faster than a full mesh. So that's what that is there. On the output tab, we have a whole list of different output files. So at the top, those are the ones that are specific to the mesh. So we have STL mesh, which is for like Gmesh. Those don't contain the material or property information, but they are mesh files. We have a mass file. So I guess this one's actually not a mesh file, but the mesh information is used along with your material and property information to try to calculate the mass of your tri and beam elements and your total mass there. That's what's shown on the bottom right here. We then have the nastran and the associated nkey file, which allows the nodes and elements to be tagged and identified. Then we have the calculix or abacus file format. Surfaces and intersection curves, we have a few file formats for. And then at the bottom, which is the most recent addition, we have the trimmed CAD options. So the first one on there, you can just list the information that you want written out to those CAD files just to identify things a little bit better. Those get written to the various layers of the CAD export file formats. You specify your length unit. That's just going to be something that's written out to the file. Then we have IGES and step options. We have some more options for the step file. We have a tolerance that just gets written out to the file. That's supposed to, just tell the file that you're importing it to when to consider points that are close together as the same point. I believe that's what that's used for. We then have a shell representation or a brep solid representation. Last, for the GUI tabs, we have the display tab. So this is going to be available after you've actually generated a mesh. It allows you to visualize the triangle elements, the cap elements, things like that. So we have a draw mesh, color elements, draw nodes, draw element orientation vectors. So this will show a vector that identifies how each triangle is oriented. So this is going to be used for things like composite layups and things like that, I believe. We color everything differently so you can identify them. You can't change those colors. There's no user control for that, unfortunately, at the moment. But in the display element set, you can show or hide any of your sets of elements. So you can hide the OML, you can hide a certain spar, things like that. We then have intersection curve display information. So this is really important if, especially for trimmed CAD exports, if it doesn't work for some reason, you could come in here and try to take a closer look at some of those intersection curves and see if something went wrong. Things to look out for are, jagged intersection curves, gaps in your intersection curves, things like that. If that does happen, you might just need to adjust your geometry slightly, move the location of an FEA element, or FEA part, things like that. If you do have mesh issues, that's kind of the approach that I would suggest. Just, move things slightly so it doesn't really change the overall design, but helps alleviate these mesh resolution issues. So here's just an example of an analysis that was done. So created a structure in OpenVSP, exported it as an FEA mesh. Here we're showing the visualize nodes option, and I used the clipping tool to have a little bit of a view of what's inside along with the OML. We then imported that to Calculix, did a really simple, setup of the load condition or the load nodes and the boundary condition. The primary purpose of this was not really to, assess the results of the analysis, mostly to just check, when we apply a boundary and load condition, does the mesh stay together as we expect it to? Do we have that correct connectivity there? If you could see here with these exaggerated deflections and displacements, we do keep everything together. I wouldn't focus too much on the values of the results that you're looking at. This was just done to prove, yes, we have the connectivity that we expect. And so you should be able to use this tool for, a more detailed analysis if you'd like. So the next thing I'm going to talk about is two of the, or at least one of the newer additions, two different ways to do it. So we have CAD exports available. You can do untrimmed CAD exports, which is going to give you something like what you see on the bottom right. So when you're adding FEA parts and you see them in the 3D view, those are just cutting planes, and when you export them as untrimmed, they're not going to be trimmed against the surface or anything like that. They're just going to be exactly how you would see it in the 3D geometry view. They're not intersected with the OML or anything like that, but it does at least get you the representation of where you put these different cutting planes and things like that. More recently, we've added trimmed CAD exports, and so this will take that representation that we saw earlier, intersect everything, and only leave what's inside the OML. There are some limitations. It does not actually split the surface where those the parent surface where those FEA parts are placed. That might be something that we'll work on improving in the future, but at the moment, this is how it's done. Subsurfaces, those are just exported as surface curves, so the surface isn't broken with where you place your FEA subsurfaces as well. And intersections between FEA parts, like, I'm not sure if you guys can see my mouse, but something like this where we have the spar intersecting the rib. This is not breaking up the rib into a leading edge surface, a middle surface, and a trailing edge surface. It's still a single surface, and we just identify this intersection curve as a surface curve in the export files. Other things that, these are all things that we might be able to do to improve the tool, but at the moment, this is just what to expect. Main purpose of this is to be able to, use external meshing tool to generate your desired mesh. So if you want a quad dominant mesh, this will be the approach that you need to take right now. A couple of bugs to be aware of. Sometimes if you have parts that are coplanar, what we try to do is check for those and merge them to avoid issues with the mesh algorithms just crashing because it can't determine an intersection, or at least a single intersection curve between two coplanar parts. But the problem is if you have something like a spar that you have limited to your inboard section and your outboard section, but they're still on the same plane, it will try to merge those, and it'll turn them into a single FEA part instead of having one just for the inboard section and another one for the outboard section. So that's something to be aware of. There are some issues with the trimmed CAD export with having the FEA parts confined to a certain section, or for when symmetry is on. So if you look back at an image like this, all these cutting planes are oversized slightly. And so when you have something like a spar, it's actually going to be oversized into the symmetric copy. And if you have it limited to a certain wing section, it'll be slightly oversized into the next section. When we triangulate it, we just get rid of those triangles that are outside of that. But this leads to problems when we're doing trimmed CAD exports where we're not really throwing away those surfaces correctly. So that's something to be aware of. It'll work really well for if you have turn symmetry off and if you just have your spar not confined to a certain section. So just some things to note, but we'll be working on improving those. A couple of improvements, I mentioned a few of them on the previous slide. There have been a few other suggestions that I've been told of. So an option to set a rib on the total or sectional root and tip. Right now you have to do it manually, and if you are going to put a rib on your wing root or tip cap, make sure you turn the caps off first. Otherwise, that'll lead to potentially a coplanar intersection issue. If you have rounded tip caps, that's a little bit different. But if you have flat tip caps, that will be an issue. So turn them off if they're flat and you're placing a rib there. Like I said, we talked about improving some of the trimming algorithms for these different FEA parts. And then I also mentioned earlier the issue with ribs rotating them when you have a dihedral or anhedral. Right now, you'll just have to use a rib type to model them instead. Or excuse me, a slice type, I meant. And then the last thing I had here is just a list of the API functions along with where to find them in the API documentation. There are two examples you can look at. One of them in C++ is the API test suite. There's an FEA mesh test in there. We're working on developing a more complete test suite for FEA mesh. Then in the scripts directory, there's a FEA mesh VSP script you could take a look at. And like I said, there's an analysis in process or test suite in process, and there's also an analysis in process. So instead of using these functions, the API functions specifically for FEA mesh, you'll be able to use the analysis manager. So we'll have a string associated with this FEA mesh analysis, and you'll be able to run it through that way. Any questions before I go through a little demo?
Yeah, we've had a handful of questions here online, and we've been answering them live as best we can. We just had one asking how the mass of the tries can be calculated if the thickness of the shell, say the rib spar, the skin, isn't necessarily specified. Is that more up to the FEA tool?
So we do calculate it in OpenVSP because you assign a thickness to your property, your shell property. I could just pull that up in the GUI to show you. But if we go to FEA mesh and we look at the shell property, it has a thickness associated with it. So yes, it's a shell element that has no thickness, but since we're assigning it this property, we can calculate a mass using the material that's associated with this property as well.
Thank you.
Yeah, you're welcome. Well, all right, well, I'll go ahead and start off with the demo here. So I will add a wing structure. What I'm going to do is I'm going to break it into 2 sections. And feel free to interrupt me at any time if there are any questions. I'm going to go to Analysis, FEA Mesh. From here, on the Structures tab, I'm going to add the structure to that wing. And then I could click this Orient Wing button. That'll show the dgen geom preview from top down. If you want to change back, you could go select the geom, go to Normal, and go back to Wire. I'll leave it in that dgen geom preview for now. Here's where you select your different unit system. I'll leave it just as is. Next, I could start adding FEA parts. So the first one here is the skin. As I mentioned earlier, it just has this remove skin tries option. I'll go ahead and start off adding some spars. So this one, I could call it, just clicked on edit part to pull up the parameters. You could also double click and that'll pull up the parameters for it too. I'm going to call this the trailing edge spar, and it'll be the inboard one because we have a 2-section wing. So after naming it, I'm going to click this limit spar to section option and see how it will just confine it to the first section. I could have it for 2 sections. If you have a 5-section wing, you could have it even just between 2 of those sections or 3. But I'm going to have this just on the first section for now, and I'll put it somewhere like 0.75. Next, I'm going to add the outboard trailing edge spar. So I'll add another spar. It'll, whichever one I have selected, it'll update the FEA part edit GUI to correspond to it. I'll call this one trailing edge spar out. I'll limit it to the second section. One thing to note is if you try clicking here, it won't let you have the first section be greater than the end section. This is something especially that's come up when you're modifying things through the API. You have to update the end section first before you can update the start section. And I'll make that at 0.75 as well. So now you can see I have 2 different spars, one for the inboard, one for the outboard section, but they'll be connected at this break in the wing section. For the leading edge spar, I'll just keep that one as a single, across all sections. And I'll put that at something like 0.25. Now what I'm going to do is add a rib array. Similar, I could do this one just for demonstration. I'll have it in the first section, and then another rib array for the second section. This one I'll decrease the spacing a little bit. whoops, increase the spacing of it. Something like that. I'll look at the top view again. There we go. I'll call this rib array in. The next rib array I'm going to add will be the outboard one. So a lot of what I'm doing is just for demonstration, not necessarily representative of any wing structure that you'll be modeling. But this one I'll have just on the second section. In here, one thing I could do is I could say leading edge to be perpendicular to, the trailing edge to be perpendicular to, or I can pick any of these spars that I've added. So I'll just have it to the trailing edge for demonstration. Things like material properties, things like that, I'm not going to worry too much about them right now. I could always go back and update them later. What I'm going to do next is I'm going to add some fixed points in this area, maybe on the bottom wing surface, show kind of like a attachment point, something like that. So if I go to fixed point and add, so that's going to be moved in UW coordinates. So I'll have to move it out first, and then it'll wrap around the bottom. And I'll just place it somewhere like there. I'll just place another one real quick just so you guys can see the results. Maybe something like that. So I have two fixed points on the bottom of the wing there. Maybe it'll be attaching something like an engine. I don't know. But that's what that'll be. You can also, like I said, change if you want it to be on any of your FEA parts. Another one I could show is, real quick, how about let's add a rectangle subsurface. So just the regular subsurface modeling capabilities that you have with other geoms. And then I'm going to show you the this cap no tries option. So maybe this will model like an access panel. And we're going to just have basically a hole that's punched in the top of this wing. Make it a little bit smaller maybe. Yeah, something like that. Okay, so there's the quick demonstration of a representative wing model, or not so representative wing model, not sure, but that's what we have here. Then just briefly, I can show you the materials property tab. I could add a new one if I like. If I had a specific material I'm trying to model, I'm just going to use the defaults that are available here. And then on the properties tab, I could change this. If I want to make the skin a little bit less thick, or I could add a completely new one. Same with the default beam elements. Going back to the parts tab, right now we have just the kind of default settings for the shell or cap properties or assignments and the associated properties. You can't assign a cap property when you don't have either cap or shell and cap selected. But one thing that's really neat about this is you can select multiple at the same time. And even if you have one like a fixed point that can't have a shell or cap property associated with it, I could still go ahead and select multiple at the same time. That'll update here. I can assign a cap property or a beam property to all of them, things like that. So that's what you could do in this part tab instead of having to open up each one individually and change that. For the rectangle, I'm going to change that back to cap. So this is going to remove the interior triangular elements. I'll leave the mesh settings the same, just since I'm working in the the kind of the default scale of everything. Output files, I'll turn these ones off for now. I'll demonstrate a separate trimmed CAD export. I'll just leave the mesh files for now. And then display, this will populate once I click the mesh and export button. Just for the sake of time, I'm going to turn symmetry off, and that should get rid of all the FEA structures on that side, and this will run a little bit faster now. I could have also just clicked the half mesh button. Same thing. So mesh and export should go pretty quickly.
Hey Justin, while that's working, someone asked on the social Q&A if you can have multiple beam properties set to different beam elements. So if you can have, can you make your own properties out of different thicknesses and materials and apply those to different elements?
Yes, you can make your own properties. Like if I just came in here, select beam property, click add, I could change the material. I could change the cross-section type, change its width and height, and I could assign that to, an individual rib cap. I can make a line array and assign those elements there. That's what you could do. But you can't assign maybe like part of the rib cap as one property and part of the rib cap as another. Hopefully that explains it. But here we see the result from the mesh. Have a couple of pretty thin triangles, things like that. I might want to adjust my mesh settings to solve that. But everything's connected at least. We could go to the display tab and hide the skin if we like. I can also show you here, we have where I said cap and no tries, we have a hole basically punched in the top of the wing. You can still see the ribs on the inside though. And also that the cap from those ribs was not actually, removed from the inside of that as well. So that's what that capability is. If I go to the bottom of the wing where I put those fixed points, you'll see they are nodes at the in the mesh. So that worked correctly. The mesh fixed those as we intended. The spar that I had as a two-section spar, if I turn off the skin, that should be connected correctly as well. So yeah, there we have it. Just a quick example. It's definitely limited in some ways, but it's definitely could give you a good starting point before you move on to more advanced tools. And if you do need some of the more advanced tools, that's what M4 is going to be talking about next with their Structure Studio. So this is what you could do within OpenVSP, just using the built-in capabilities. But
Justin, would you demo taking that to CAD real quick?
Yeah, so this one I'm going to pull up a different model, just because this one had that, or I could at least just change it real quick. But remember how I mentioned that issue when we have spars that are on one section and another?
As long as it doesn't crash, I'd say show it with the issue. It'll help explain the issue.
Okay, I mean it won't. The step file probably won't open, but I could still export it.
Then go ahead and show one without it.
Okay. Yeah, usually the Aegis file might open correctly. Those usually have better luck. But what I'm going to do is just change the spars. Let me show those. I'm just going to change this one to be a full to go across the full span, and I'm going to delete the other one. Let me show the wing. There we go. So I could go to the display settings and click reset display if I like. That'll get me back to where I started when I was editing those FEA parts. So this one should be, I think I accidentally deleted the wrong one. I'll move this one back to be the leading edge bar. Don't worry about the name conventions at the moment. And this one should be also across the full span. I'm going to delete the rectangle as well. I'll hold off on that one, but I'll go to export CAD. Actually, let me change the output files first, and I'll go through export CAD, which you can also do mesh and export if you have these selected, but this will just skip the mesh triangulation if you are just going straight to CAD. I'd look in the terminal that pops up. There could be some error messages. Looks like we're okay for the most part. The one thing that I'd be concerned about if I'm exporting to STEP or IGES is if you see any error message that's like a failure to close loop, things like that. I'll pull up FreeCAD. This is using Open Cascade, so it should have similar behavior as a couple of other open source CAD programs out there. Go ahead and find that step file. Yep, that's the one. Should be the same as the IGES as well. But if all went well, should have everything trimmed correctly. Let me turn the transparency up. So there you can see everything's been trimmed against the OML. We might have some issues if you zoom in closely on some programs. Sometimes, since the wing surface is not broken up by these ribs as well, the ribs aren't really fully connected to the wing surface, so that is a limitation. Hopefully we'll be able to improve it soon. But that's just something to be aware of. Some programs might have better experience with it than others, but by all means, please let us know if you do use this capability. Let us know how it works for you. Very happy to hear about it, and know if there's anything we can improve. So probably just about low on time now, so if there are any questions, please feel free to ask. I don't know if there was anything API related that was asked earlier that you guys might want me to answer.
Considering we only have about 3 minutes to get M4 spooled up, you can continue answering some of the questions in the live chat or the social Q&A. But I think we'll, I'll just go ahead and say that, really appreciate you taking the time to demonstrate those features. FEA mesh is just one of those really cool things in VSP that they should be really proud of, because it's exceptionally useful and versatile. So thanks for taking the time, Justin. I know we've had you on for quite a long time today, so yeah, go ahead and enjoy the break for the rest of the afternoon. And Tyler, are you on? I think I saw you join the meeting here recently.
Yes, I'm here. Can you hear me?
I can hear you fine. I think your audio is coming in nice and clear. You're welcome to go ahead and share your desktop. We've got about 2 minutes or so before we're going to roll into your presentation, just so that we stay on schedule for those watching online.
Alrighty.
All right, and for our next presentation on the schedule, we're going to be allowing M4 Engineering to provide their presentation on the M4 Structures Studio. With us now is Tyler Winter from M4, and he's going to introduce these concepts, and then we're going to have some additional presentations kind of following along. So they're blocked out for about 2 hours here, and they're going to use this chunk of time to try and spread the various topics out. We'll have a couple of breaks just for questions to try and sneak in here in the middle for everybody online that's following along. But Tyler, I think if you are ready, you're welcome to go ahead.
Great. Thank you, Brandon. All right. So as Brandon said, we've got the next 2 hours here. So this first hour, I will give an overview and updates for our M4 Structure Studio software. And if for those of you not familiar with M4 Structure Studio, it's our physics-based weight prediction downstream analysis tool of VSP. And we will discuss the workflow on some of that here momentarily. After that, Thomas Nishinzi will discuss really some new kind of exciting updates for the tool, which we're calling our Sketchpoint layout tool inside of Structure Studio. And then in the second hour, Thomas will continue to give an overview of our sketch model UI capabilities. And then lastly, Joe Robinson will finish up with a UAM demonstration of a side-by-side helicopter. Okay, so let's get started. Okay, so for my talk, I'm going to give the overview of Structure Studio. I'm going to walk you through the workflow, the typical workflow for a user, and then also discuss kind of briefly our capability summary, highlight some of the selected applications, and discuss recent developments and some future work. Okay, so when we think about developing structural models and doing physics-based weight prediction, you know, the motivation or driving kind of force for this is basically because we don't have necessarily all the data we need to come up with these really nice empirical relationships that predict weight, like Nicolai or the Raymer equations and whatnot, especially when we deal with unconventional vehicles. So the idea is for these unconventional vehicle designs, we can start with a concept in geometry, say in OpenVSP, and proceed down a workflow where we're laying out kind of in this stepping stone image shown on the right here, kind of through the process of constructing the structural layout, developing the FEMMesh, the aerodynamic panels for loads and boundary conditions, you know, your materials, all the things that you need to actually size an unconventional vehicle. And so Structure Studio really has been in development over the last 15 years, and I've been leading the team probably over the last 7 or 8 years now. And we've done a lot of work with OpenVSP, and we think it's an excellent geometry modeling tool that allows for acceleration of this kind of conceptual design level weight prediction capability. So now I'm going to discuss the workflow for M4 Structure Studio. So as you can see at the top here, going across the horizontal, we've got kind of 6 boxes there, and we start at the left with our Sketchpoint layout component. And this has been completely overhauled. I don't want to steal Thomas's thunder, but I will say that for those of you that were following our work and the Structure Studio tool set in the past, you would have noticed that we were doing a lot of development inside of our customized version of VSP. And now we are no longer doing that. We are using the Python API from OpenVSP, and we've fully integrated that within our workflow and our software now. It has a number of advantages for doing that, but I won't steal Thomas's thunder, so he can talk to that a little bit in the next talk. But this is the first step. So the first step is laying these what we call sketch points or structural hard points on your vehicle components that you've created in VSP. And for each of the components that you want to actually generate structural representations for. And so in this step, we also have capabilities for doing automated layouts, including automated wing layouts and automated fuselage layouts. And those essentially allow the user to very rapidly kind of have a predefined template for laying out their wing and fuselage structures. And as kind of we like to think of it as more of a starting point to really get into the details but it allows you kind of to get up to speed and kind of create those very rapid layouts. The next step is what we call sketch. And this is a very detailed step involved in the workflow where you're going to go through and you're going to assign all the material properties. You're going to identify all the structural components in addition to any that were defined during your automated wing layout or fuselage layout usage. And then in addition to that, this is also where you're going to detail the analysis cases or the jobs that will be run for your optimization routine. And in addition, you will also define, any attachments and things like that that will essentially allow you to build up your sketch for each component that you're interested in modeling structure for and connecting it together into a final kind of complete vehicle FEM. So once you've done that, the next step is really we've kind of combined these next two blocks here, what we call FEM and merge. And this is essentially where the software will go on and take all the information that you defined in SPL and Sketch, and then take that information and go off and generate a finite element model that for each of the individual components with all the details that you specified included, and then merge it into a final vehicle FEM, kind of shown here in the bottom center. Is an example of like our XB15 model. And so moving on, once you have your FEM, it's important to note that this FEM is what we call optimization ready. So all of the analysis cards and details that are important to running an optimization routine are set up and constructed in a way that essentially are ready for immediate execution within Nastran. And I guess I'll point out just briefly that we do both support NX Nastran and MSC Nastran versions. But yeah, once you get to this step, essentially you're ready to run your optimization and size your vehicle structure subject to the load cases that you're interested in considering. Once your Nastran job is finished, you can run a post-process step, which is called weight, which allows you to generate a comprehensive weight statement. And essentially, this is a kind of a customized weight statement that we've created that breaks down not only all the individual component mass property information, but also the vehicle as well as other items that are interesting to report, such as CONM2s associated with attachments and things like that. And also we give a property summary. So when you construct all your properties for your vehicle, you can see what each property weighs, its thickness, what you had as like a baseline, and what the optimized thickness was to kind of give you very quick kind of informative feedback on whether or not your optimization went well and makes sense. And yeah, so that is essentially the workflow. So we have those six steps that finish at weight. And then moving on, I'm going to now discuss our capability summary. So this chart's a bit of an eye chart. I do kind of highlight now in four component blocks here. You can see the various capabilities of each component as you move through the workflow. And so I guess I'll give a little bit of a background on, prior versions of Structure Studio had the Sketchpoint layout capabilities all done within OpenVSP. And now essentially you would basically just bring your VSP file once you're ready to start modeling the structure directly into our tool. You wouldn't need to do any Sketchpoint layout creations within VSP anymore or use our customized version, because now all of those capabilities have been ported into our tool. And then moving on to Sketch, again, like I said before, this is where you really specify all the details. For material specifications, we have support for composite ply layup specifications, as well as rapid loads modeling. A lot of the work we've done in the past year or two now has been focused on rotorcraft features, adding additional rotorcraft features, thanks to support from NASA and Army Ames. And then in addition to that, we've also enabled a lot of viewing different visualizations that are within the GUI that I think Thomas will touch on a little bit in his talk. And then lastly, you can still run, execute, FIM, merge, and wait all from within the GUI. So kind of you can think we've really consolidated all of the capabilities into kind of a one-stop shop. Once you're done setting up your VSP model in VSP, all you have to do is save it and then just bring it right into our tool, and you're ready to start structural modeling. So then lastly, I think I touched on some of these things already for FIM and merge and wait. I will point out for the FIM, the types of analyses that we support: normal modes, linear statics, aeroelastic analysis, both static and dynamic flutter. Also, and obviously design optimization, which is what we're really after to get those size thicknesses for our vehicles. Okay, so I'll move on here and show kind of just some selected applications. The first one we'll start with is a conventional MD-87 vehicle that we looked at, and what you're seeing here is an animation where we're showing a trade between fuselage height and fuselage length, and we're kind of marching along the exterior of that design study envelope that we looked at, where each case that you're seeing here was generated with the tool and fully executed through Nastran with a size optimized result to a given stress allowable that was specified for this vehicle. Our next application we'll show is a low boom vehicle that we looked at, and similarly this is another one where we did a walk around the envelope of looking at fuselage height versus fuselage length, and again each one of these are a fully sized optimization result from Nastran. Okay, so this result here is basically a flutter result that we're showing from an electric GA application. I believe this was shown last year. This was a really nice result that where we did a sizing condition actually based on flutter, and so these types of things are possible with the tool and work pretty well. And then lastly here for the selected applications, just we've really looked at a lot of vehicles, many more that are even shown here. This is what we're allowed to show. As you can see on the left, we've looked at some VTOL UAM type style applications there in a previous phase 3 that concluded last year, and then we've also looked at kind of some traditional transports as well as GA and HAIL type vehicles. In the center there, you can see. And then on the right side, you can also see some missile rocket concepts as well as some blended wing RLV applications and even satellites, along with the Uber configurations there as well. So lots of different applications we've looked at with this tool set. Okay, so moving on to some of the recent developments. So we have been, I guess I'll point out first that we are working halfway through our CCRPP effort that was funded thanks with support to NASA, Langley Ames, and on Army Ames. And we've extended a number of different features and enhancements to the tool set, and we're still in the middle of doing that. Kind of the big feature that came out within the last year was our support for the Mac OS platform. We also have slated to look at Ubuntu next. And then moving on here, again, as I mentioned prior, there's a lot of enhancements to the UI. For any of you out there that have actually used the UI or looked at the UI in the past, you'll notice that it's been completely overhauled, shown there on the top right image. It has a lot of more streamlined functionality in it. As I mentioned, it can import VSP files directly. And then we have kind of a new and improved sketch point layout capability within this UI as well. And then many bug fixes. And then what else? Other additional demonstration cases we've been looking at. So the CH-47D shown there on the right, and the MV-22. And we're also looking at a structural increment for a rear ramp for that MV-22 configuration as well. We did have a presentation at AIAA Aviation back in summer, and we did recently get a paper accepted into SciTech 2021 for those of you that are interested in learning more about our work. Okay, so for future work, just kind of a brief overview of that. So as I mentioned, we're halfway through the CCRPP effort. We've got three more demonstrations that we're going to look at for structural increments, including the RVLT-B Hector there, shown on the bottom right. As I mentioned, support for Ubuntu platforms coming in the near future. And we're also working on a crashworthiness capability that will support our extension of rotorcraft features and integration with industry standard rotorcraft tools such as Ixgen, RCAS, and CAMRAD 2. The other thing that we're exploring is academic licensing options. We've been in discussion with a few professors at various universities and are hopefully exploring that option as well, and much more. All right, so with that, I think we've come to the next part of the talk here. So I guess we can roll to Thomas.
Yeah, Tyler, for I've got echo coming through there. That sounds like it's gone now. Someone has asked what you would recommend for system requirements in trying to run M4SS.
Yeah, so the system requirements, we have them somewhere. I don't have them handy at the moment to give you the exact details, but the requirements are not very high. Obviously, if on the software side, one of the big hurdles that a lot of folks have to overcome is the NASTRAN requirement. So I'll say that, or echo that again, is that you'll definitely need NASTRAN. But if your machine can run NASTRAN, you probably can run our tool. It's not excessively high on the requirements as far as that goes.
But it was originally Windows. Now it's Windows and Mac.
Right. Yeah, we support 64-bit Windows and Mac, and Ubuntu's coming soon. Is there any other questions?
Nope, you can go.
So Brandon, should I switch over so Thomas can take over?
Yeah, I think let's see. It's only about 20 after 3. I think we've got the questions in the live feed, and we're doing all right in social Q&A. For the time being, depending on how long you think it might take Thomas to get into his material, we can keep going. But as far as the UAM demonstration side of things, we'll try and start that right at 4 o'clock to stick on the schedule. So we can probably go ahead and just roll into Thomas's stuff now, and then we can pause sometime.
Okay, sounds good.
Hello, can you hear me? Okay. So let me try and share my screen. All right. So I think I'm going to be going over the sketch point layout tool and then the sketch tool within M4 Structure Studio. I think the plan was to start sketch at 4, but I think that'll probably be moved ahead at this point. But I'll just get into the sketch point layout tool now. Or should I start now? Or
You can just go ahead and start with the sketchpoint layout demonstration.
All right.
The way we have it blocked out at 4 o'clock is for the UAM demonstration. So um, it seemed like it. So would this be the beginning of that content, the UAM demonstration?
The beginning of that content was supposed to be M4SS sketch, which is like part 2 of my presentation.
Okay, yeah, so we can go ahead and start doing the layout demonstration, and then we'll start the sketch side of things at 4 o'clock.
Okay, sounds good. All right, so hello, my name's Thomas Nishenzi. I joined M4 back in January, and I've spent most of my time since then working on Structure Studio. So I'm going to be going over the parts of Structure Studio that are used to define the models and as such require the bulk of the manual input. So first module I was going to talk about is the sketch point layout module, or SPL. So just as an overview, I'm going to be giving a brief overview of sketch point layout tool to begin with. Then I'll be talk about how OpenVSP models are imported into Sketchpoint Layout Tool and how the Sketchpoint Layout Tool uses them. Then I'll give an overview of what Sketchpoint layouts are themselves, which is the core of the SPL module. I'll then go over some of the automated tools that are included in the Sketchpoint Layout Tool. They make the tool a little easier to use for the user. Then I was going to go over how the Sketchpoint Layout Tool is used to create the sketch model, which will be used in the sketch module of M4 Structure Studio. And then before I get into it, and then that the M4SS sketch overview will start at 4 o'clock, followed by the UAM demonstration. So here's kind of a 4-step process of using this tool. You start with the OpenVSP component. And this OpenVSP component is built by the user before, it doesn't even have to be built with Structure Studio in mind. You can just have it ready. Then in the Sketchpoint Layout Tool, sketch points are added to the OpenVSP vehicle. And that's what I'll be talking about during this session. Then after that, the sketch point layout is converted to the sketch model. In the sketch model, all the structural, aerodynamic, and load cases are defined. And then finally, that sketch model is used to automatically generate a Nastran-ready finite element model. So those of you familiar with M4 Structure Studios might be surprised that by the existence of this new module, this Sketchpoint Layout Tool. Previously, M4 utilized a branch of OpenVSP called M4SS OpenVSP that contained its own Sketchpoint Layout Tool. Although we enjoyed OpenVSP, we found maintaining the Structure Studio branch of OpenVSP to be cumbersome, and in the end, did not provide us exactly what we wanted from it. And what we really wanted was a streamlined tool solely for creating sketch point layouts. M4SS OpenVSP was not this, and more often than not, created complexity instead of simplifying things. So this brings us to the new M4SS sketch point layout tool. I'd like to say that this tool was made possible with the improved Python API of OpenVSP. Unfortunately, its development began before the API documentation became what it is today. So it was a little difficult on that front. And then at the bottom of the slide, we have a comparison of the discontinued OpenVSP branch with the new Sketchpoint layout tool. As you can see, we tried to copy some of the look and feel of OpenVSP, but keep in mind that the Sketchpoint layout tool is in no way a replacement of OpenVSP. It requires the user to import a pre-made model and contains only functionality related to placing sketch points. some benefits we achieved by transitioning to the Sketchpoint layout tool is that we unified all the functionality of Structure Studio into a single application, which streamlined the user experience. Additionally, users can now simply use the latest version of OpenVSP as soon as it's released and not have to wait for us to update and build the M4 branch. So now that I've gone over this little history lesson, we can go into exactly what the Sketchpoint layout tool is. So I'll start talking about importing OpenVSP models. So as I said, M4 Structure Studio utilizes the Python API of OpenVSP to import models. What this means is that Structure Studio has a direct access to the underlying shapes and parameters of the OpenVSP model. This would eliminate any model translation and healing that may be required by other tools. For example, some tools might require a step file. This would mean that OpenVSP first has to convert the model into step format, and then when that external tool reads step file, it then converts it again into its own format. And this can sometimes require some form of geometry healing. So like I said before, M4 Structure Studio is able to utilize the OpenVSP model directly, eliminating any need for model healing or translation. Now that the OpenVSP model is inside Structure Studio, Sketchpoint layouts can start being defined. So Structure Studio is used to predict structural weight. However, it isn't able to do that without any user import. It needs some information about the vehicle to make physics-based prediction. This information starts with the user-defined Sketchpoint layout. Each structurally relevant component requires a Sketchpoint layout, and each Sketchpoint layout contains a single sketch plane and a list of sketch points. These layouts are used to locate structurally relevant points of interest on the OpenVSP model. Additionally, we provide the user with a limited access to the underlying OpenVSP model, such as tessellation parameters. So the first part of the Sketchpoint layout is the sketch plane. I find the idea of the sketch plane to be a little abstract, but its goal is to simplify the process of defining 3D structural elements. So the sketch plane, or maybe you call it a modeling plane, is a 2D plane that when looked directly down, shows the full depth structure. For this wing example, I've defined the sketch plane as the XY plane. This allows the pattern of ribs and stars to be placed as shown the red lines on a 2D representation of the wing. And when the time comes to generate the finite element model, it is able to define the structural layout of the 3D wing. So now then after the user has defined the sketch plane, they can start defining sketch points. Sketch points are placed directly on the OpenVSP model. Sketch points can be defined one of three ways. First is free points, which can be placed individually and placed anywhere on the component. Lines are defined with a start and end point, and any number of sketch points can be distributed between them. Finally, we have grids. Grids can contain any distribution of non-parallel or parallel rows and columns, and a sketch point is placed wherever a row and column intersect. Just as a further note on lines and grids is that they can be drawn straight in either parametric space defined in OpenVSP, or they can be defined as being straight in coordinate space. This just provides the user with an added layer of control and conveniences to the Sketchpoint layout. The sketch points themselves are the core of any model in Structure Studio, as they are we consider them the common building blocks of the model. Basically, all spatial, structural, and aerodynamic elements within Structure Studio are defined with the use of sketch points. I'll get into how they're used exactly in the sketch module of Structure Studio, but I've listed a couple of examples here. So like lines can be drawn between sketch points to define ribs and spars or bulkheads and floors. Triangles and quadrilaterals defined by sketch points can create skin boundaries and aerodynamic panels and control surface boundaries. while individual sketch points could be used to locate attachment points for non-structural masses and various other elements. One final thing to note about sketch points is that as they are defined as being on OpenVSP components, they will go along for the ride, so to speak, as OpenVSP parameters are modified. This allows Structure Studio to be used in design space exploration applications. So if the model changes, you won't have to go in and redefine all the sketch points. The sketch points are defined with their UW parameters, so they follow along. So now I'll go over some of the automated tools included in the sketch point layout tool. The first automated tool is the automated wing layout tool. The automated wing layout tool lets the user specify desired number of ribs and spars, and it automatically generates a corresponding sketch point layout. And if the resulting layout isn't quite what you want, you can go in and still edit the layout itself or add and remove sketch points. You can angle the ribs and spars as well. So the other automated tool we have is the automated fuselage layout tool. The automated fuselage layout tool lets you define the number and parametric location of bulkheads and the number of axial stations between the bulkheads. Again, after the tool has been run, you can further go in and edit the sketch point layout to make it more what you want. So finally, once you've finished your sketch point layout, and you can use that sketch point layout to create a sketch model. So the sketch point layout models are converted to sketch models with a click of a button. It takes the 3D sketch points on the OpenVSP model and projects them onto the OpenVSP degen geometry corresponding to the sketch plane. And this creates a 2D representation of the model that will be used to define structures and load cases. The conversion process also automatically generates a basic structural model, and it includes a normal nodes analysis in the sketch model. So at this point, I think we're going to wait until 4 o'clock for the next section, where we'll go over sketch and the UAM demonstration.
Here, let me turn the mic on both. We had a question on the social Q&A that, let's see. Oh, no, that's already been answered. Okay, never mind then. Let's see, anything in the live stream side? No.
We had a question earlier about the earlier structures, which I answered about the VSP stuff, but it was concerning interpolating arrow loads and arrow data from an arrow mesh onto an FEA mesh, and about different techniques for that. And of course, the VSP, say VSP arrow structures mesh is completely independent. I'm sorry, the VSP arrow aerodynamics mesh is completely independent from the FEA structures mesh in VSP, but the Nastran tools that you guys are going to have tools to map arrow loads to structures. So if you can, you might speak a little bit about what about that, or if it's going to be covered later, about how arrow loads are mapped to the structural mesh in M4's tool.
Yeah, thanks, Rob. So since you're utilizing Nastran, for subsonic analysis, it has a doublet lattice capability inside of Nastran that we'll use, and that essentially within Structure Studio, how we connect the arrow loads to the structural FEM is we have Nastran uses a spline, various spline capabilities for translating those loads to the FEM. And we have actually built in the M4SS sketch, you will be able to define those splines and the actual aerodynamic panel model itself within our tool. in kind of an abstracted but similar to Nastran, because at the end of the day, that's obviously what's being created is the Nastran representation of that. So.
Thanks, Tyler.
And as a quick reminder to anyone out there listening that might not be following the live chat, on the 2020 OpenVSP workshop page, that's the wiki page, ESAero has put together a feedback form that we'd appreciate you fill out if you have the time, so that we can know how we did, how the quality was, if there were any talks that you were really interested in, and suggestions or requests for things that you'd like to have covered. And just below that is a link to an attendance sheet. If you care to fill that out, all the stuff in there is optional unless you want to be added to a mailing list, in which case please include your email address for us. That one does have a password associated with it to keep the bots out, and that's here in the live chat link. So it's hashtag VSPWS2020, and that's in the text right above the link. So you can just copy that in and paste it, and it'll take you to the attendance sheet. And we should have somewhere in the neighborhood of about 20 to 25 minutes or so until we need to start up the 4 o'clock presentation. So if you're following along on the social Q&A or following on in the live chat, and there's something that you would like to see demonstrated, perhaps something with the API that Justin could show quickly, or something of that nature, just go ahead and remind us in those feeds, and maybe we can take some time to do a quick demo while we have our intermission here. All right, everybody, it's 4 o'clock. Hope everybody had a nice break. We're going to go ahead and continue on with the M4 Structures Studio demonstration with the sketch features. So the audio should be good. If I can get a nice audio check from Thomas, we'll go ahead and go.
Yeah, can you hear me?
Can do. You're welcome to proceed.
All right. So welcome to part 2 of the M4 Structure Studio block. We're going to be starting with an overview of M4SS Sketch, and then Joe will lead us through a UAM demonstration of the tool. So, like I said, my name is Thomas Nishenzi. Last section, I went over the M4 Structure Studio Sketch Point layout tool, and then this section, I'm going to be going over the Sketch module. So first, I'll be giving an overview of how the M4SS Sketch fits into the larger Structure Studio workflow. Then I'll give an overview of what sketch models are and how they are defined by the user. Finally, I'll talk about the different component and analysis cards that can be added to a sketch model. And these cards will be what define various structures and load cases in the sketch model. So here we have, again, an image representing the Structure Studio process. First, we start with the OpenVSP model. Then in the sketch point layout tool, the user adds sketch points to the surface of the component. These sketch points are the common building blocks in Structure Studio, and they're used to define various structural and aerodynamic features, as well as define load cases. Third, we transition to M4SS Sketch, where cards are used to define all that model information, such as property regions or aerodynamic panels. And Sketch will be the primary focus of this talk now. And then finally, Structure Studio takes all the information defined in M4SS Sketch and uses it to automatically generate a Nastran-ready finite element model. So now onto sketch models. Here we have the Structure Studio UI. Right now we're looking at it with the sketch model view activated. Every part of the sketch model is defined with sketch cards. For example, to define a material, you would add a mat card, or to define a control surface, you might add a control sketch card. So on the left of the UI, you can see the sketch model tree, which contains all of the sketch cards. Beneath that is the properties editor. This is where you would define all the fields of the sketch card. Then taking up the majority of the UI, the model viewer. This provides a visual representation of all the sketch cards that have been added to the model. Something I'd like to point out again is that when the sketch model is finished, Structure Studio uses all those cards to automatically build a Nastran-ready BDF for the vehicle. So here we're taking a closer look at the sketch model tree itself. At the top are merge cards. These cards define how Structure Studios should merge the component level finite element models together and the order that they should be merged in. Beneath that are where the analyses are defined. Sketch models can contain any number of analyses, and each analysis can have any number of subcases. This model, for example, shows three different analyses have been defined: a normal modes analysis, a design optimization, and an aeroelastic flutter analysis. Then within each of these analyses, additional sketch cards are added to define various parameters, loads, or constraints for the analysis. Underneath the analysis section, we have the components. These components were grabbed directly from the OpenVSP model. And then within each component, there's various subcategories of cards. Subcategories are aerodynamic elements, materials and properties, the modeling parameters, points, which will contain sketch points, and the structural elements. Then all of these cards sum up to make the complete component level model, and then together all these component level models make the complete vehicle and sketch model. So previous users of Structure Studio may have been a little put off by our old sketch model UI. So I'd like to go over some of the improvements we've made over the year. Cards can be added to the sketch model through context-sensitive pop-up menus. Similarly, cards can be removed by right-clicking on them and selecting delete. And finally, cards can be edited with the properties editor. Together, just these three functions are all you need to define a complete sketch model. And that sketch model will be ready to generate a Nastran-ready finite element model. Furthermore, the model tree is color-coded to help troubleshoot any problems with the sketch model. Within the tree, all sketch cards are highlighted in green, while branches that are simply for organizational purposes are not highlighted. Then the colored circles can be used to locate any potential problems with the sketch model. Any card marked red will tell you what is wrong and will need to be modified or deleted from the model. Cards that are marked yellow were recently added by the user and simply require a quick review by the user to verify that the fields were defined correctly. And then finally, when all the cards are marked green and every desired sketch card has been added, then the model is valid and can be used to generate the finite element model. So now I'm going to go over some of the more commonly used component cards. So here are some of the structural sketch cards that are used to define structural elements in Structure Studio. First, we have the skin card. These define the regions where outer surface plate elements should be added. In the bottom right image, you can see that the whole model has been paved with the blue skin 4 quadrilaterals, which translates to the fully defined outer surface fuselage shown in green. Beam and frame cards are used to define internal plate and bar elements. Beam elements are defined as a line between 2 points, which translates to a projection of plate elements through the model, and that's shown in an example of that shown in the upper right. Frame cards translate to bar elements for the model. They can be defined a number of ways, and that's shown in the bottom left. And then finally, you can add attachment and landing gear cards. Attachments can be used to rigidly attach non-structural discrete masses, such as stores or engines. The LDGR card, or the landing geared car, is a version of the attachment card that was designed specifically to model the extended landing gear of the vehicle. There are other structural cards, but these are just a few I wanted to highlight. Next, we have materials and properties cards. Material MTRL or material cards can be used to define isotropic or orthotropic materials. The prop or properties card utilizes material cards to define isotropic shell, laminate shell, or isotropic bar properties. On the right, we can see a composite layup defined by a prop card that contains different layers of various material cards. Finally, we have the prop tag card. This card does not actually affect the analysis in any way, but allows the user to group different property regions together for weight statement reporting. So, for example, you might want to know how much all the internal structures of the wing weigh. So you would group all those property regions together with a single prop tag. Then, when the weight statement is generated, you would then be able to view all the masses as a single mass. Next, we have aerodynamic cards. The Aero4 and Aeroparam cards are used to define vortex lattice elements and splines. These can be used in aerostructural analyses. Additionally, the user can define control surfaces with the control card. Currently, users define these cards just like any other card, but hopefully in the near future, we'll have the capability for directly utilizing control surface definitions from the OpenVSP model itself to create these cards automatically. So if you have a detailed OpenVSP model with several control surfaces, you would be able to directly import them into Structure Studio, which would save you hopefully save you a lot of time. Finally, I'm going to talk about some of the analysis cards that can be added to Structure Studio models or sketch models. Analyses are defined with analysis cards, and subcases are defined with case cards. Each analysis has a Nastran solution tied to it. Currently, we support linear statics, normal modes, static arrow elasticity, arrow elastic flutter, dynamic arrow elasticity, and design optimization solutions. We plan on adding a buckling solution type as well. Additionally, there are 22 unique cards available to define various analysis parameters, constraints, or loads. On the right, I've included an example set of analyses for a sketch model. This model contains 5 different analyses. Each has their own set of subcases. And basically, Structure Studio allows the user to quickly define any number of analyses for the model. So I'm going to go over a couple of the analysis cards available in Structure Studio. This is just some of the more common ones, or a select subset. The first card I'd like to talk about is the load card. The load card can define many load cases for various types of analyses, and it's as varied as can define loads as varied as a point force load to a flutter load. On the right, you can see how the surface pressure card was used to define loads acting on a region of elements. Below that, you can see how point force and point moment might be used to provide load cases for a rotorcraft. And here are just a couple of other analysis cards. The fuel card can be used to define fuel loads on the aircraft. Depending on the analysis, this can be defined as a distributed mass, force, or pressure on an enclosed surface region. Additionally, it automatically takes into account the volume of the fuel and utilizes the defined acceleration to see how the fuel itself pools within the tank. Slungings are used to create case-specific non-structural weights. This allows the user to include different non-structural masses for different load cases while maintaining the same vehicle model. On the right, we can see the fuel card acting on different regions defined by the tank card. And then below that, we have an image demonstrating a slung with a 3G jump analysis. So to summarize, the sketch model is initialized from the sketch point layout model, which places sketch points on OpenVSP components. Sketch provides a simple card-based framework for creating Nastran-ready finite element models. And then these sketch models can contain both the component and analysis cards, where the component cards define structural and aerodynamic elements, and then the analysis cards are used to define Nastran solution types and various parameters within that load case. So there are 6 different types of solutions available, and then 22 different analysis cards can be added to them. And then multiple analyses can be added to any model. So that concludes my portion of the talk, and I think I'll be handing it over to Joe now, who will talk about a UAM demonstration of Structure Studio.
Thank you, Thomas. Joe, are you ready to share your screen?
Yep, I'm ready to go here.
Okay.
Okay.
All right. Are you ready to go?
Yep, let's do this. All right. Hello, everyone. I'm Joe Robinson from M4 Engineering. And so far, we've learned about what M4 Structure Studio is and how you make a model in it and how you bring that over from OpenVSP. And today, I'm going to go over sort of the how and sort of what that looks like. Yeah. And we're going to do that using this urban air mobility side-by-side helicopter demonstration, which is developed by NASA. And so we're going to start out here on the right with this OpenVSP model that came from NASA Ames. And what we're going to try and do is get a minimal structural weight, and we're going to have various load cases relevant to this kind of a configuration. So we've got here like a tandem side-by-side rotor, 6-passenger helicopter type configuration. So we're going to break down a little bit of what's in this OpenVSP model and which pieces of it we're going to use in size. So in the dark blue boxes here, we see the components that we're going to create structural meshes for and that we want to size in an optimization. So that is the fuselage and the wing strut. We're also going to mesh some components, but leave them at their baseline values and not size them in the optimization. So that here we're doing the horizontal tail and the windshield, which is sort of that front portion of the fuselage there. And then we've got some other components that we're not going to model structures for, but we are going to include as non-structural masses. So the landing gear, the rotors, and the engines, and things like that. Okay, so one of the first choices to make when making a Structure Studio model is a material system and applying those to the different regions. So we've gone here with a carbon composite layup for the fuselage and the wing strut. And internally, we've got aluminum ring frames and beams. And we can see the windshield here in green. It's going to be a plexiglass type material, and we're not going to size that. For our material layup, we've gone sort of a standard carbon sandwich here with UD on the outside, and then alternating plain weave carbon plus minus 45 and 090, 3 plies each, and we've got a symmetric layup here. And then for our optimization, we're going to size those outer carbon UD layers to give us our optimized design here. In addition, we're also going to size the aluminum frames with the radius, so they're represented as rod elements. All right, so our non-structural masses, luckily here we have a lot of good sources for our non-structural masses, and we've broken them down into the groups here. All of these are using either the attachment or the landing gear card, which are point non-structural masses, and then we're going to rigidly attach those to various components. So you can see mostly the fuselage and the wing strut here. All right, that's it. Okay, so load cases here. We're looking at a couple of typical helicopter type load cases. We've got a 2G jump, which we're going to represent on the bottom left there with point loads at our rotor centers. And then we've got a 1.33G landing, and we're going to represent that with loads through our landing gear we defined. So on a configuration like this, the wing and the tail keeps moving, they don't have very large areas, and so we don't expect like a pull-up type maneuver to be very significant for the structure. If you're looking at something like a tilt rotor, that's definitely something to keep in mind. You can use both of these like helicopter type load cases and aero trim cases, like a pull-up or a pushover type maneuver. Okay, so now we're going to go through, we sort of defined what our model is going to be like, how we're going to pull it together, what load cases are significant, and now we're going to talk about how do we make that in M4 Structure Studio. So just a reminder here of the basic process. So we started at the sketch point layout, where we take in our OpenVSP model, and we're going to put points on it. And those points are going to represent our structural hard points, where we're going to attach masses, where we're going to define internal structures, those sorts of things. Then we do the majority of the work in our sketch module here. We're going to define those materials, those load cases that we talked about, and we're going to set up our analyses. Then FEM and merge are the automatic components. So we're going to mesh our geometry and then merge all the components together. And then finally, we'll run through Nastran to do the design optimization, and we'll post-process that and get a weight statement. Okay, so the first step on that process, the sketch point layout, we've got our 3 components here that we're making structural meshes for. So that's the fuselage, the wing strut, and the horizontal tail. And here we've laid out sketch points. So this step and the next step, you can kind of think of them in tandem, because you're going to want to place your points at the locations that have significance in the structure, and we'll see sort of how we've chosen those in the next slide. But most of the time, fuselages and wings, you want sort of a grid of vertical and horizontal lines of points that allows you to make your standard structures like ribs and spars and frames and bulkheads. Okay, so here at the sketch step, we've got all of our sketches laid out. So here, the wing strut and the horizontal tail are quite simple structures. We've got the blue rectangles here represent our skins. So these are going to be our upper and lower skin OMLs. Those will be represented with quadrilateral shell elements. And they're going to have the carbon composite materials. On both the horizontal tail and the wing strut here, we have an array of spars and ribs. So we've gone with a 2-spar design with evenly spaced ribs on each. It's a pretty standard setup. I think the most interesting one here is on the fuselage. So again, we've gone with the skins for the OML here, but we've got some more interesting internal structure. So at the very front, the red line, we've got a bulkhead. Where we have these red horizontal lines, we're going to get internal floors. So we've got a floor here for the cabin, and then we've got sort of a ceiling, which is going to be where some of our large masses are. We've got an engine and those kind of large mass items up there. And then where we have the orange double lines, we're going to have ring frames. So we're going to have a series of those that run through the fuselage here. Okay, so once we've defined that internal structural layout, we run through our automatic process here and we get a mesh. So you can see on the left, we've got the OMLs of all of our components. In the center bottom here, we can see our internal structure. So we've got the beams and ribs of our wing strut there. We can see the bulkhead and the 2 floors that we made. And then you can see the rings in a little more detail in the top right here, the teal. So we've got rings that go around the OML of the fuselage, and then we have a couple of beams that cross through our floors there as well. All right, so let's go into some Nastran results here. So this is for our sized structure. And we're looking here at fringes of max and min principal strain, which is our criteria for a composite layup material. And we can see this 2G jump, which is where we're putting load through the rotor hubs vertically. We mostly get strain in our wing strut, which is what we expect. We can see the top and bottom there. We get peaks near the inboard sections. So the way we broke this up property material wise is there's a series of materials span-wise out the wing strut, and those are sized independently. And so we see we get a couple of sections of high strain where those materials have sized down to the minimum to meet our allowable criteria, and then also give us the minimum weight. For this configuration, the landing, we don't see very high strains here, and so we don't get much of a sizing impact from this load case. Right, and finally here we've got the weight results. So we have some published estimates that we're comparing to here. and we see most places we're pretty close. We're a little bit lighter on the wing strut, about 17% lighter. Horizontal tail, remember we did not size in this example here. Probably we'd need some other kind of a load case to better size that, for example, an abrupt pitch maneuver or something like that. And then overall, we end up with quite a close result. As I mentioned, there are a few enhancements we could do to this kind of analysis. So if we add some more load cases, we could size that horizontal tail. And we're working currently on some different types of rotorcraft load cases, including crash scenarios, which are often critical for many structural elements. And then additionally, we're currently in work on integrating with some rotor-specific analysis tools, such as RCAS, where things like the whirl flutter for the rotors may become a critical load case. And so we may see a modification when that feature is implemented. Okay, and I'll go through some future work and conclusions based on this demonstration problem here. So as I mentioned, we have crashworthiness loads modeling in the works as part of our CCRPP effort for NASA. And we're also integrating some rotorcraft tools that will allow us to model and analyze rotor structures and analyze them in combination with fuselage structure. So we'll be able to combine the effects of rotor fuselage interaction, that sort of thing. So we've given a workflow of M4 Structure Studio here today, and we've gone through a modeling approach for the UAM side-by-side rotorcraft. We've looked at some preliminary results for sizing, namely in the wing strut, and we showed pretty good agreement, but there are elements that we could improve with some more features which are in development. And yeah, I want to thank the NASA SBIR program and the CCRPP from Ames, Langley, and Army Ames, which helped fund this research. And that concludes the M4 Structure Studio section. So if you want to get in contact with any of the speakers here today, or M4 Engineering, you can look here.
All right, thanks, Joe. That's a really good demonstration, and it kind of shows how you can stretch your legs with M4 Structure Studio and get it integrated with Nastran and do some of this really interesting work. So I really appreciate you guys taking the time to demonstrate and talk about the software, and really great advancements leveraging the API and making it a standalone tool. So really congratulations on all that work.
Thanks, Brandon.
Well, to everyone listening in online, by all means, if you have some questions for the M4 folks, type it into the live chat or into the social Q&A. We might be able to follow up on some of that. Also, if you have questions stemming from any of the talks or presentations here over the last 3 days or so, feel free to chat with us for a little bit. We're about a half an hour ahead of the 5 o'clock cutoff, so if there's something that kind of stuck in your mind and you still want to see, we might be able to have a little bit of a demonstration here with the time that we have left. Let's see. Let me go ahead and exit out of full screen for the time being. Well, So far, not seeing any takers on the social Q&A or the live stream. I don't know if Rob, you're seeing or hearing anything different, or Justin.
Nope, looks like there's nothing coming up yet.
How much lag is there to the? Okay, here's one.
Yeah.
Question. Okay, so I'll answer the first one. To Juan, the nice animations that Dave Kinney was presenting from VSP Aero. The version of VSP Aero that we distribute doesn't have that built in. Dave Kinney uses a different library for taking built-in screenshots, and I don't want to build and distribute that, so I rip it out. So he takes screenshots. I'm not sure whether he has that automated or whether he does it manually, and then he uses a command line program outside of that to stitch it together into a video. Well, I'll add that to the list. Maybe Justin, we should that list I sent you, maybe we should add to it. We've been talking about getting it so that the VSP viewer uses the same library as OpenVSP, so that we don't have the library dependency problem that I've been trying to avoid, but we can get the videos back in. So we'll try and make that easier so that we can make those videos, because you're right, they're compelling for the unsteady cases.
Yeah, I agree. I'll add it to the list.
The next question, it is correct there's sort of two answers. If you're using OpenVSP's finite element structure modeling, each structure, each sort of assembly is built around one component, which is the trimming outer surface, the OML. And so you build a structure for the wing, you build a structure for the fuselage, you build a structure for the tail. You can even build multiple structures for a wing. You can have a primary structure, and then you can go back and have another structure for the flap and another structure for the leading edge. So those are not in the built-in VSP tool. Those are not in any way connected to each other or intersected with each other. You can do multiple of them and then export them separately, and then in your finite element tool, connect them together. And that's certainly one use for the key points that Justin was talking about, where you can use those key points to then insert rigid elements to transfer loads between those components. And that's often the way that you would do a model, because you probably don't transfer a load directly through the skin of a wing all the way to the skin of a fuselage. Instead, you have your primary structure that goes to some fittings, and those fittings are hard points on both sides, where you have ring frames and other things that come together to transfer load into those fittings, and then you're really trying to carry the load there. So on the other hand, the M4 Structure Studio does have the ability to model multiple structures, and they have the tool that they talked about for merging those structures together, merging and joining. And so those, they do have that ability to do multiple structures. So it's a bit more sophisticated. There's a question about how to model liquids in OpenVSP, and specifically for fuel. So earlier today, there was a question about fuel tanks, and I mentioned conformal geometry as a way to do that. Let me do a very quick demo with conformal geometry, just to show a wing fuel tank. I know, Scott, you're a space person, so you'd rather put fuel tanks in cylinders, but we'll put it in a wing real quick. So here's a wing, and just for fun, I'm going to look at it as a transparent wing. And I'm going to go ahead, and we want a little bit more. For this, we probably want a bit more thickness. So I'm going to make it an 18% thick airfoil, just for that argument's sake. So here's a nice fat wing. And conformal components, if you pull down, and it's this just above the line, if you choose conformal, what it does is it's a shape type that derives its shape from another shape. So when you choose conformal and you say add, what it does is it adds the shape as a child of it. So I'm going to go ahead and shade that, and I'm going to make our conformal component ruby, so it's nice and red. And what you see here is we actually have the red surface is an offset surface inside of the wing. And what we can do is, if we want that to be a fuel tank, we can come to the design tab and we can trim it. And so first we'll trim it in the chord and say we want that to be the minimum to be at 0.25. And so that would be our aft spar, and only go up to say 0.8. That would be our forward spar, maybe 0.85. We can get away with that. And then our fuel tank, maybe it doesn't start, so we're going to trim it in the U direction as well. It starts at say 0.2, and maybe it only goes outboard as far as 0.7. So we can do that to build a representation of a fuel tank in a wing. And then in this case, what I'm going to do is I will use sets to add that to set 0. And so now if I go and I do my comp geom, and I say I only want to do comp geom on set 0, and I execute, then it's going to come and calculate my volume of that component, 15.63. Likewise, I could come and say, okay, my conformal component, I'm going to show everything here. My conformal component, I'm going to increase its priority. We didn't talk about mass properties much, but I'm going to increase its priority, and I'm going to say that the density of my liquid, if the tank is entirely full, let's say the density of my liquid here is 3, and the wing is going to be a lower priority. It's stay at 0, and its density is 1. And so now if I do mass properties, and I do that mass properties analysis, what we've actually done is we've calculated the mass properties of the full wing fuel tank and the lighter density wing around it, and the total mass is 21, and the moments of inertia and the CG are all properly calculated. I've actually developed an algorithm to look at fuel tank mass, moments of inertia, and CG location as it fills from empty to full. So if you have some really strangely shaped fuel tank, especially say a wing with dihedral and sweep, if we come in here and we want to show all these again, if we come in and we put in a bunch of dihedral, we'll say, right? So let's crank it up 15 degrees of dihedral. You can imagine that and while we're at it, let's go truly nuts and let's put in a lot of incidence, 25 degrees of incidence. So you can imagine this wing, it has a very distinct, this fuel tank has a very distinct low point, this corner down here. And so as it fills up in the Z direction, you're going to have a center of gravity of the fuel that's going to start down here and work its way up to a centroid point, and it's going to follow some path, and the moment of inertia of that tank is going to change. So I've actually got some code that does that kind of calculation, Scott. If that's useful to you, we can try and prioritize making that available. It was a part of an earlier generation of mass properties revamp that never was ready for prime time and never got released. So let's see. So you can do, I'm looking at Sibin's question about a prescribed wake for the rotor. I'm not sure if Davis thought of that. I'll pass that on. We do find with experience that these VTOL vehicles, the interaction of the wake with the rest of the vehicle is one of the most tricky parts. So it might be useful occasionally to have a prescribed wake, but I think it'll also be, you'll find very quickly that it's limiting. If you are doing a isolated rotor, Justin mentioned this, if you are doing a rotor alone, then you might look at using the steady rotating frame formulation, which is documented on the wiki, or sorry, on the GitHub page, because that is a very computationally efficient way to do a rotor. Okay, so we've got a question about how to use fit model to fit an airfoil from a scanned wing or propeller, if it is possible. Thank you. So what I'd really just suggest, if you're trying to fit a full wing or a prop from a laser scan, worry about the airfoil last. What you're going to want to start with is getting the leading edge and the trailing edge correct, and getting the plan form right, and getting that shape. And I would go so far as to say, maybe really go to extreme lengths. Just ignore the fact. Just use a NACA airfoil. Get the leading edge matched up, get the trailing edge matched up, and get to where you're very, very happy with those. Once you've done that, sort of to Andy Hahn's point, once you're close on the wing, Fit Model's job is a lot easier. So once you're close there, then I would probably actually go, and if you knew it was one of the existing airfoil families, certainly use that family. But I would start by simply trying to match the thickness and get the thickness about right, and then maybe match the rest of the shape. And if I was doing that, I would use the Kulfan, the CST airfoil type. That class shape transformation, if you're not familiar with it as airfoil types, this CST airfoil, this one allows individual sort of, we're at the root here. Let me move to the, we're at the tip. Let me move to the root. The CST airfoil allows the most localized control, and that'll be the best for some sort of a least squares fit to a cloud of points. So, but do that last. Get the leading edge and the trailing edge right, get the plan form really well matched, then match the thickness, then convert that foil to a CST, and then adjust the top and bottom surface individually to match.
And if I could add on to that as well, I think, sometimes it's hard to really back out exactly what the foil is, and maybe even a CST might be a bit too far in the other direction. If you're trying to just get it to where it approximates whatever the airfoil looks like, you can usually get that plan form out of either picking a NACA 4 series or a 6 series, whatever flavor you like, and just letting it float through some of those parameters as well. So if you find one that it's in a class of airfoil that is pretty darn close, you can play with far fewer parameters and get something really close to what you need. There's a good questions coming into the live chat. Let's see.
Yeah. So Russ just asked about the lift equivalent area in the wave drag. So right now, I'd say there's no plan for that. You should be able to take and run the VSP arrow in supersonic mode to get the nose to tail lift distribution, and from that compute the lift contribution to wave drag, which and also then the lift contribution to the sonic boom. We don't have any current effort on that at present. Certainly the pieces are there, and with the right people motivating and funding it, that would be something that would be possible. Okay. Justin, somebody has asked a question on the social Q&A about the Python API. They're getting a file not found, parasite.png, except it's spelled wrong. I'm not sure what on earth in the API would be trying to read in a PNG file. Justin, do you have any comments for that?
No, I don't think so. I'm not actually seeing the question either. Oh, I see it now on the conference IO. Yeah, I am not really sure what's going on there. If the user who posted that could provide some more information on exactly what's going on, is it when you try to import OpenVSP? Is it when you're calling a particular function? everything like that. If you could provide that information, better place to post it might be on the Google group, but at the moment, I'm not aware of that error or how to solve it.
Okay, someone just asked, I was typing in an answer, but what airfoil family do you recommend for a tilt prop rotor? I'll just say that historically, most propellers for propelling an airplane use either a 1.6 series or a 6.5 series or a combination of those two. Most helicopter rotors use various rotors that are specific to helicopters. There aren't parametric families of them in the same way that there are the other NACA foils. Those airfoils are designed for lower moment coefficient typically, but they're also for very, very high, helicopter rotors are very high aspect ratio, very flimsy, very floppy, low solidity rotors. Tilt rotors are somewhere in between. The V22 uses a custom airfoil. And so, yeah, Daniel Shield mentioned that. The XV15, there's a lot of airfoil data available about the XV15 airfoils that NASA developed with Bell before the V22. And that rotor went through many revisions from the beginning of the development program to the end. There's a book by Harris, a NASA publication by Harris, that is a compendium of hover test stand data for props and rotors that includes a lot of those different steps in the XV15 rotor that specifies the foils used in them. So I recommend you look for that report by Harris. The early ones used, like I'm saying here, a 1.6 series and 6.5 series. The later ones went to proprietary airfoils that were developed by Bell.
Okay, yeah, Justin, he said he was running the test dgingiom.py, so I see that there was an answer to that already.
Yeah, I posted it in there. Really not sure about that one still. I would suggest, just opening up a Python interpreter, making sure first you can import OpenVSP, and then from there, just try like a simple function call, like, vsp.addgeom with wing. If that's all working, then it's probably a bug in that specific Python example that we could look into. But try those out first.
So I've got a question. I'm not sure who, since it's on the social Q&A, I'm not sure who's asking it, but I mentioned on one of these platforms earlier in the workshop that Uber has, and I have this idea of a community built tool validation project. And I mentioned that as something that's hopefully in the works and coming. So the idea of this project would be an open source project. It'll be on GitHub. But instead of focusing on source code, it'll focus on aerodynamic test cases. And since Uber would be doing this, it would be mostly focused on UAM test cases. And the idea would be that we would provide the geometry, the input files, and the test conditions for different tools to be compared, and then leave it as an open project so that developers of different tools, whether that's Flightstream or VSP Aero or Charm or RCAS or high fidelity CFD tools or students at a university or whoever's developing aero tools trying to meet these UAM aero modeling challenges, would be able to use their tool on the test case and then push that result up as a contribution to the GitHub site. And the idea would be that they would not only put up their results, but they would also put up the input files so that it would also become a self-documenting set of best practices where the developers of these tools sort of show you how they would use a particular tool to tackle a particular problem. And the idea would be that we would add, it would be a growing list of projects that would start, and it would include everything from simple rigid body, fixed wing, stability and control, type things like we saw some of today, all the way up to very complex interacting unsteady flows with rotors. And then, as I said, it would be a place for tool developers to go and show off what their tool can do, and also a place for the UAM community to sort of pose challenges and show the kinds of perhaps weaknesses that current tools have, because there's so many unique needs from UAM that it would hopefully help drive and motivate the tool development to conquer some of these challenges. So that's the idea.
All right. Let's see. Yeah, there's still some going around with the API stuff on the social Q&A. Watching the live chat to try and see if there are any other questions here. We've got just under 10 minutes before the scheduled close of the workshop, so I guess now's as good a time as any to thank everyone for your attendance and your participation in these events and these talks. We really appreciate that you've taken the time to see what's going on and to give us some feedback and to ask the questions and show us what you're interested in. So we really appreciate that, and hopefully you had a good experience this year. We were doing our best to try and pivot away from an in-person event, which is traditional for this workshop, and hopefully you've had a good experience and that everything came through relatively clear. But we'll see what happens next year. I think that we've shown that we can at least leverage the technology that we have to try and make this reasonably accessible and easy to do here. So again, thank you to all of our presenters for giving your time and your dedication in trying to make this a really successful event. And I know I really enjoyed all of the talks, showing what everyone has been doing with OpenVSP over the last year, particularly the cool features that everyone has done. So a big thank you to all of our presenters, and of course to Rob and Justin for helping me organize this event and to scheduling everything out. So big thank you to everyone for that. But unless Rob or Justin, either of you guys have any closing remarks, we've got a few chats coming in, and we really appreciate all of you as well. So
Go
ahead, Rob.
Thanks for everyone for hanging with us. It's been a long 3 days. If you have the opportunity, do go over to the attendance survey. Let us know who you were, where you're from, who you work for, what your interests are, and we'll appreciate that. And otherwise, we'll hopefully see you in person at the next one, and maybe find a way to stream it as well.
And I was just going to add real quick, thank you, Rob and Brandon. You put a lot of work into this. I think it turned out really well. The OpenVSP community, I'm sure, is very grateful for getting this all set up and everything. So thank you very much.
It's a great tool. I think that it's incredibly versatile and powerful, and for where it lies in the design space, it ticks all the boxes, and it just keeps getting better, and that's the great thing about it. So what a few days it's been. But everyone out there that's following along, thank you again for watching, and we really hope you enjoyed it. By all means, stay safe. That's kind of the name of the game right now. So take care of yourself, and all of these sessions are recorded and stored. You can follow the session links to get back to any of the replays to the videos, including the live chat. The videos themselves will be hopefully broken up into different sessions so you can quickly link to it. But follow the Workshop 2020 page for updates on how to find the information quickly, and we'll be sharing some slides and documents that we can get from the presenters so that you guys can have those as well. So with that, it's 5 minutes to closing time. There's no problem at all with finishing just a little bit early. So thank you, everyone, and stay safe. We'll see you around.